All right. Yesterday we started talking about series, and if you remember, the difference between a series and a sequence was we just added up the terms, right? And so we looked at our formulas yesterday. We have our two S sub n formulas. The first one is for a arithmetic series, when you're summing up the first n terms. The second one is for a geometric series, when you're summing up the first n terms. And then we started talking about an infinite series. So if you remember yesterday, we did some of this on the calculator yesterday. We looked at 2 to the 10th. We're doing this in the calculator?
Oh, yes.
And then if you remember, we looked at like 2 to the 100th, and you remember that was really small. And then we looked at 1/2 to the 1,000, and we learned that that was really big,
Really small.
right? It was so big, it was 300 zeros. It was such a small, big number. Don't feel bad. The other class did the exact same thing. We did that, and like, oh, that's a really big number. Okay. Actually, it's lots of zeros, but it's really, really small, right?
Yeah.
Okay. So what we want to look at then is how we can find the sum of an infinite series. Okay. So what I want to do is I want to write our formula for S sub n from over here, but just put n there, not write it down. Okay, so what I mean there, my first term, this is the formula I'm using, is that formula, and that would be 1/2, 1 minus 1/2 to the n, 1 minus 1. Now, what I want you to notice here is this. From what we just did, consider this 1/2 to the n right here. If n is 1,000, that number is this. Even if we go 100 and use that number. Even if we go 30 and use that number. I think we all could agree as n gets bigger and bigger, this 1/2 to the n gets really small, doesn't it? Effectively, it gets so small that it goes to 0. If you have 0.00000, however many you have, that basically is 0, right? Now, it's not exactly 0, as we looked at some incredibly big, small number. But it's really close to 0. So if this part right here goes to 0 and goes away, and I can erase that, notice what my formula becomes. We get this formula right here, which is our formula for our infinite series. Okay. Now, let's do another one here. Let's look at this one. First, I want you to consider, what's the r here? What do you multiply by to get the next term? 3/2. So if I write that one, does the same thing work? What happens to that is I put in a really big number. Does it get really small again? It gets really big. How do you know it's going to get bigger?
Because it's
Because it's greater than 1. This blows up, I'll say, gets big. So what that's going to do is it's going to change what we have based on our r. Okay. So when we get to our formula here, we're going to have two possibilities. If our r is less than 1, and it's the absolute value of r, so it could be -1/2 or +1/3 or whatever. If it's less than 1, we say our infinite series converges to this formula, and so we're keeping the same formula. That should be an A. If your R is greater than 1, it diverges. Now, those are two fancy math words. If something converges, what does it mean?
It's bigger.
Converges, it gets close to something, right?
Yeah.
So it's coming together. So if it converges, it goes to a number. If it diverges, that means it goes away, gets bigger, doesn't go to anything, there's no answer, right? That would be like here. If we add these up, more and more terms, they just keep getting bigger and bigger and bigger. So as you add them up, it doesn't equal anything. Here, if I add them up, more and more terms, because they're getting smaller and smaller and smaller, this will equal something. So let's do this one. My sum, my S, and notice there's no number here. We're not looking at n now. We're looking at all of the terms. Here's our formula. 1/2 over 1 minus 1/2. So our answer is Q. What's 1 minus 1? So the sum of that infinite series let's have you try one. 27, 9, 3, and 1. First step, figure out what is your R. What do you multiply by to get the next term?
1/3.
1/3. So there's your R. So now we're using our formula for the sum of an infinite series. Put that in. Plug it into your calculator. Grab one if you need to grab one. What do you get?
Number
What'd you get? I got 26.6.
6.
That's right.
How did you get that? I got 40.5.
27 divided by 2/3.
Make sure you use parentheses
On the bottom.
around the bottom. You see what
On the whole bottom.
Oh, the full bottom?
Yeah,
Full bottom.
the whole bottom.
Muffled and the key bottom.
All right.
Okay, sorry.
The second thing I'm going to look at here today, and the homework I passed out, there's 6 of those. Those are pretty simple. Just plug them into the formula and put them in check. We want to talk about sigma notation today. And I know you've seen this in Algebra 2. And we're just going to kind of look at it kind of quickly here today, kind of introduce it. This is one of those topics that they will throw something like this on the ACT at times. These are really easy once you've seen them. And if you've never seen them, it makes absolutely no sense. So what a sigma notation is this symbol right here. And this symbol, this kind of capital E looking thing, is a Greek letter right here. It is the capital sigma. For those of you that have had stats, you'll remember lowercase sigma represents standard deviation, right? This is capital sigma, like that, okay? So, and this means, from statistics, this is a math symbol that means sum. So sigma is kind of the Greek letter for S. So this symbol means summation or sum. Now, when we work with this, we're going to have some variable at the bottom, 1 equals k. It's a sum number at the top. This is doesn't look like it. This is a shorthand mathematical way to write a series. So let's look at an example. We have the summation of k equals 1 to 4 of k squared. So what you do is you start at the bottom at 1, and you plug 1 in for k. That's 1 squared. Plus, you now go up to the next number, 2, and you plug 2 in. You get 2 squared. Then you put 3 in, 3 squared. Then you put 4 in, that's 4 squared. So we stop at 4 because the top number is 4. This would give us then 1 plus 4 plus 9 plus 16. That would be expanded form. Okay, we're just expanding. Okay? When I look at your homework here, one of the things it says is to write each sigma notation in expanded form. Okay. Now, if you want to evaluate it, we just add all those up. 1 plus 4 plus 9 plus 16 is 30. And then that is evaluated. Some of your homework problems say expand the first 4 terms and then evaluate the sigma notation. Let's try another one. Sigma notation of k equals 3 to 6 with 2k plus 1. So you start at the bottom number, which is 3, and you substitute 3 in. Plus, you go to 4, plus, you go to 5, plus 6, and we stop. Notice here, here's the one mistake people make a lot. They look at the top and they say, there's a 6, therefore I should have 6 terms. We don't have 6 terms, we only have 4. Because we started at 3. 3, 4, 5, 6. That's only 4 terms. Now, if I evaluate, or at least multiply these out, simplify them, that's 6 and 1 is 7, 8 and 1 is 9, 10 and 1 is 11, 12 and 1 is 13. So you can see from what you did before, what type of series is that? 7, 9. It's arithmetic. I mean, if you really wanted to, you could go back and like sum it up with the arithmetic formula, but it'd just be easier to multiply those out if you had to, or sum up if you had to evaluate. But now we have infinity. So when it says expand, can we expand the whole thing? So on your homework, what it's going to say is write the first 4 terms. So just do that here. Write down what are the first 4 terms of this sigma notation. So try that. Your first term is
1/3 to the 1 minus 1.
1/3 of the 1 minus 1, which is 1/3 of the 0, which is just 1. Plus, the second term would be 1/3 plus, and then Noah's dot. How do we evaluate that now? Add all this up. How do we add up it? If we only had a formula to add up an infinite geometric series.
Yeah, I know, right? It's different.
And we just did that 5 minutes ago. So what is our R? What do you multiply by to get the next term? 1/3. What's our first term?
1.
1. So this is going to be 1 divided by 1 minus 1/3, which is 3. Now, let's go back to this one. Having done these in algebra 2, if you were looking at this one and I said evaluate, what do you remember about doing these in algebra 2?
No. I don't think I'm-
There's one big thing that I was hoping you at least remembered this.
I don't.
It's been a while since I've been out here too.
I don't remember learning this one.
I'm pretty sure you might have even done it like while you were online last year.
I remember us doing it in class, and I probably.
And I just remember this because I remember Luke doing it last year. Maybe he was just cheating and you weren't supposed to do it that way. Which is possible.
Very close.
I don't think I could.
Probably.
That is, this is built into your calculator. So if you go to your calculator and you go to math and you go all the way, it's actually quicker to go up.
Summation.
And you go to summation. Now, the variable you use does not need to be the same variable. So on this example here, I used k, right? I could put an x in there, and this still will work with x. So we're going to talk about that in a second. Now, notice this will give you 30, right? There's no way to expand it. So as we do this, I am okay if you use this to evaluate and help you that way, but we want to understand how to expand these and understand what that means, okay, as we do that. So, that one, be similar, right? Type it in. How would you do infinity? How do you think you could do that? I'm going to say it a different way. How do you think you could approximate it on your calculator? Just put in a big number. So, just go to your calculator and do x is 1. I don't know, let's go 100. 1/3 to the x minus 1. Now, I'm guessing for many of you, based on your calculator, if you just did what I did, it probably didn't go that quick. It might have taken longer. And you got to be careful, because what happens if you're like, oh, let's make this number a lot bigger? Right? If you make this too big, it's just gonna, your calculator's gonna sit and spin for a while while it figures all that out. Okay?
Yeah.
So, and your calculators are not as fast as mine is even, because mine's on the computer and it's not the small calculator. But now it's just gonna spin until it eventually finishes. So, you wanna pick a big number, but don't pick too big of a number, otherwise your calculator,
Overflow.
it won't overflow.
No,
I got an overflow.
Oh, you got an overflow at what number?
I got one.
10,000?
Okay, so you didn't get, mine worked. Took a while, but it worked.
Yeah, I got an overflow.
So, okay. That's one way to do infinity. But if you are asked to evaluate an infinity, guarantee that means you can use this formula. Okay. Now, we also want to understand sigma notation going the other way. What I mean by that is if we have that series, write it in sigma notation.
Really?
No. Let me kind of tell you how to do this the easiest way. First off, here's the easiest part. Start at 1. And then what's the top number? No. What's the top number here on the sigma? This is just how many terms you have.
Oh, yeah.
1, 2, 3, 4, 5, 6, 7. Now you got to figure out the formula that goes in the middle. You already know how to do this. What type of series is this? 3, 7, 11.
Arithmetic.
It's arithmetic.
Plus 4.
We already have a formula for arithmetic. Just write down the formula. Now you can't use the recursive because it's got to go in the sigma notation. We just write down this explicit formula, which is just our first term plus k minus 1 times 4, and there's my formula. If you have an arithmetic or geometric, you do not need to try to come up with the formula and try to make this really hard. The formula's on the board that we already use, that we already know. You can just use those, okay? Try the next one.
Oh, man.
I'll give you a hint, it's plus. It goes, it's dot, dot, dot. So the top is
Infinity.
infinity.
Yeah.
How do you get one term to the next? So if you're just multiplying by 4, what type is it? Geometric. So what's our formula for geometric? Just our first term times our. No. Obviously, do I have to have the times 1 there?
No.
No, but I put it in there just to match with the forms. The only time you have to like figure something out is when it's not arithmetic or geometric. So, first off, how many terms are there?
5.
5, so that's easy. Now we got to figure out, it's not arithmetic, it's not geometric. We just got to figure out, are we smart enough to figure out how? Some people are already like, no, I can't do it. Gave up already.
Yeah, math. Is it math?
8, 27, 64, 125, 216. Those should be like jumping out and just like, and you can find the head out there. What do you say?
How was a perfect square?
No, perfect cubes, but you're close. They are the.
I knew that would got
2, 3, 4. I was gonna
You
guess.
guys help me.
I was gonna
So,
guess.
8 is
2,
2 cubed, 3
3,
cubed, 4 cubed, 5 cubed, 6 cubed. So, what goes into here?
cube.
8 cubed.
I'm gonna
It's K.
But that doesn't work.
because K equals.
Put 1 in there, what do you get? 1. Our
It starts
first
with
number is
Starts
8.
starts at 2.
So we start at 2.
1 plus 1, no.
1 plus 1 is 2.
Nice.
So you mean to start 2 here.
Yeah.
So what you're suggesting is we just put a 2 there, like that.
Yeah.
And then what would our top go be?
5 still.
5?
Yeah. No.
I guess not.
How many terms do we have? So we start at 2, 3, 4, 5.
You gotta count the number, not the, what it goes to there.
So this doesn't tell you how many terms it has. It's if you start here and you count. So the top number
Would be 6.
would be 6.
Oh, I see now.
That would work.
Yes.
Yeah.
Explain that to me?
I also could do this. I could keep it over here and just change this formula. When I put in a 1, I want to get a 2.
K plus 1.
And I could just do k plus 1 cubed. So let's pause there, look at this too.
Second one's easier.
Anything for you, Ian.
Really, you can start at any number and just change the formula so it works. I mean, if I wanted to, I could start at 3 and go to 7 and make a k minus 1. That would also work. I don't know why you'd ever do that one, right? That one's just, now we're just making it hard just to make it hard. So I don't think I'd ever use that one. But these two are both easy. Many times it's just easier to start with 1, figure out the pattern. But you guys realize right away that, well, if I just made that 2, it would make it easy. Okay. So we're looking at writing the sigma notation, understanding how to do it, expanding them, and evaluating them. Use the calculator to help you with the evaluations. I want you to understand how to use that. I know when they put, I've seen this question before in the ACT, what they will ask sometimes is they will give you something, they will give you something like this, and they will say, what is the third term? Which in this case would be 11.
Yeah.
Right? And they will do that instead of just saying, what does this equal, where you can just type it in your calculator. They'll ask you for a specific term. Okay? There's a lot more in your notes. We're going to kind of run out of time. We're not going to get into that. A lot of that kind of stuff and doing more with this stuff becomes important when you get in, for those of you going to calculus, if that's you, we'll come back to these as we go through. Okay? If that's not you, what we're doing here. Okay? All right.
Thank you.
Homework.
Quick test.
I took off all the homework.
Alright.
I took off the homework. That's the rest of the notes that we didn't get to. So, how many homeworks do we have this week? Three. What do they do? Friday, when we have the test. Okay.